In this video, we've got a really beautiful functional equation and we're going to solve it. So we've got, the question is we want to find all functions f from the natural numbers to themselves. So the natural numbers are 1, 2, 3, 4, etc. such that x f of y plus y f of x is equal to x plus y times f of x squared plus y squared for all positive integers x and y, or all natural numbers x and y. And in this video, I'm going to show you the thinking process. We're going to accumulate clues based on this equation and ultimately figure out what the functions have to be. Okay, so don't forget to hit that like button and subscribe and hype the video using the hype button if it's released recently to really help me disseminate this content and help and inspire as many people as possible in their math journey. So let's just get started and try to understand what's going on. And always the first approach with functional equations, the simplest thing to do is to plug in some values of x and y and see what information we get. Ideally small values of x and y. Okay, so let's plug in x equals 1 and y equals 1. Okay, that's the simplest value. And I'm just taking you on a journey. So I'm not showing you the ultimate cleanest solution, but showing you how to think about it, which is hopefully more fun and inspiring, and encourage you to think about it as well as we go along. So x equals 1, y equals 1, what happens is we get 1 times f of 1 plus 1 times f of 1 is equal to 1 plus 1, which is 2, times f of 1 squared plus 1 squared. 1 squared plus 1 squared is again 2. So we get 2 times f of 2. So in other words, we're going to get 2 times f of 1 is equal to 2 times f of 2, which of course implies that therefore f of 1 is f of 2. So that's really cool. Okay, so number one, we get f of 2 is f of 1. But then we can try to see how far we can keep going with this. Okay, so can we actually figure out other values? Now, to figure out a value from known values, right? If we want to figure out f of x squared plus y squared, we need to know f of y and f of x. Okay, but here's an interesting observation. So f of 3 may be a little tricky right now. How do we find f of 3? It's not quite clear, right? Because we can't write 3 on this right-hand side as the sum of two squares. But what we can observe in this situation, which is generally true, is we could keep going with this pattern. Okay, so we could sort of write, for example, 1 squared plus 2 squared. If x is 1 and y is 2, 1 squared plus 2 squared is 5. So maybe we can find f of 5. Okay, so I'm just going to write it out here. If x is 1 and y is 2, then what we can do is we can say that f of x, f of y. So we can say f of 2 plus y f of 1. So that's going to be 2f of 1 is going to equal to x plus y, which is going to be 3 times f of 1 squared plus 2 squared, which is f of 5. And observe again that we have a 1 here. We have f of 2 is f of 1, as we just figured out. So we're going to get 3f of 1 is equal to f of 5, or 3f of 5. So in other words, f of 1 is equal to f of 5. Okay, so that's pretty cool. So as you can sort of see, this approach keeps going. Okay, and the key observation here is that when we actually look at this left-hand side of this equation, if we know that f of y and f of x are the same, right? If f of y and f of x are the same, just like it was the case here that f of 2 and f of 1 are the same, then we're going to get an x plus y, f of x here. So x plus y can be factored out, and x plus y is factored out here. And let's actually just write out what I just said. So the conclusion is that if f of x is equal to f of y, then the functional equation implies that x plus y times f of x, right? X plus y times f of x in this left-hand side is equal to x plus y times f of x squared plus y squared. Okay, so we're going to get some information in this situation. We're therefore going to get f of x is equal to f of x squared plus y squared. And that is a generalization of the two steps we just observed. Okay, so I'm just accumulating clues. We don't know if these clues will be helpful or not. But what we have got is a lot of values where f is just the same thing. Okay, so that's giving us some constraints about f. Unfortunately, if we keep generating, right, we start with 1 and 1. 1 squared plus 1 squared is 2. Then 1 squared plus 2 squared is 5. Then 1 squared plus 5 squared is 26. Okay, so you're getting bigger and bigger numbers. We're not going to exhaust all the inputs. We're not going to be able to say f is the same on all the natural numbers, but we're getting a lot of values where f is the same. Okay, so that may prove helpful to us, and indeed it will. Okay, so let's now actually try to figure out some more information by, again, trying the same approach, plugging in some small values of maybe one of the variables but not the other, okay, to get more general information about the function. All right, so as I said, we want to now find out what f of x looks like for an arbitrary x. So it helps to maybe make y equals 1. Okay, so we get some information about f. So let's actually just do that. Let's put y equals to 1. And if y equals 1, then we get x times f of 1. Okay, so x times f of 1 plus 1 times f of x. Okay, so plus f of x is going to equal to x plus 1 times f of x squared plus y squared. Okay, f of x squared plus 1 squared, which is x squared plus 1. Now again, this gives us a relationship between f of x and f of x squared plus 1, but x squared plus 1 is a lot bigger than x. So where lots of values missing in between, just like we saw f of 1 is f of 2 is f of 5, we're missing f of 3 and f of 4. But the beautiful observation is, let's actually go one step further. Let's actually try to actually give a formula for f of x squared plus 1. Okay, so f of x squared plus 1, we get a formula, is going to equal to x f of 1 plus f of x divided by x plus 1. And what's really beautiful here is now this is the sort of the genius observation, because by doing this we observe something important. F is a function from the natural numbers to itself. So therefore this ratio has to be a natural number, which is giving us an information about f of x alone. And that is going to be very crucial. That is not connecting f of x to some much larger value of f of some much larger value. It's just telling us something about f of x, that namely x f of 1 plus f of x is divisible by x plus 1, okay? And this is going to be crucial. So let's now write that on the top right hand corner. All right, so I'm just going to write out our statement that x f of 1 plus f of x is divisible by x plus 1. Okay, that's our statement. Now that in itself is still not enough to know what f of x is. I mean, f of x could be a lot of possible values, right? If you fix an x, depending on f of 1, we might be able to get this a lot of times. But we're going to now do something interesting. Okay, we're going to make two important observations. The first one is going to be modular arithmetic. Okay, so another way of saying this, and modular arithmetic is super convenient, is just saying that x f of 1 plus f of x, okay, this quantity, right, this quantity I've written in red, is actually congruent to 0 mod x plus 1. Okay, so what that tells us is that the remainder when you divide x f of 1 plus f of x is 0 when you write this equation. Okay, so that's the remainder when you divide by this. And what's really cool is modular arithmetic allows us to simplify the x out. Okay, so the x basically, when you divide x by x plus 1, the remainder is minus 1. Because 1 times x plus 1 minus 1 is x. Okay, so minus 1 is the remainder when you put a multiple of x plus 1 into x. Okay, so in modular arithmetic language, we can rewrite this equation by saying minus 1 times f of 1, or minus f of 1 plus f of x is going to be congruent to 0 mod x plus 1. Okay, so that is very powerful, because that therefore means, another way of saying that is f of x minus f of 1 is divisible by x plus 1. Okay, so I'm just going to write that out in modular arithmetic. F of x is congruent to f of 1 mod x plus 1. Because their difference is divisible by x plus 1, that implies that we say they are congruent modulo x plus 1. Okay, so f of x minus f of 1 is divisible by x plus 1. So let's now write that out on what we found on this side of the board. All right, so what we've got now is we've got that f of x minus f of 1. So I'm going to write this in this notation. X plus 1 divides, this is a divide symbol, f of x minus f of 1. Okay, so that's number one. Now that tells us some interesting information about f of x. Okay, it's pretty simple. We've got rid of the x, got rid of the x f of 1, that helps. So we've got something nice and simple. And now we actually have to get one more step forward, and I want you to think, what's the next step going to be? Drop a comment down below right now. And I just want to take this opportunity to give a huge thank you so much to Alex and Stephan for ongoing support on Patreon, Nathan for ongoing gold support on Patreon, and also Aman, Rob, Shabir, Nicholas for ongoing support as YouTube channel members. All the support makes a world of difference to this channel. I can't thank the supporters enough, the exclusive perks that come with support. And if you'd like to support and make a small contribution, please consider clicking the join button down below or the Patreon links in the description. Really means the world to me and really helps me produce this infinite free accessible math education across all topics and levels. I'm a research mathematician. I do this in my own time, in my free time. I spend a lot of time to edit, to create thumbnails, to record, to come up with video ideas all on my own. And so every support helps me to possibly outsource some work and keep growing and building this project, ultimately create online courses on all the major topics of math. So if you'd like to make a small contribution and you're consistently gaining value, that would mean the world to me. So let's now get into the video. And the last observation is basically, as I said, f of x is f of x squared plus y squared for any y, right? So there are infinitely many values of f that are equal. And so that's going to be the key observation. If we apply this same rule, this is true for all x. If we apply it for, 2x squared, right? So if we put x equals y, right? So I put x is equal to y, then I'm going to get f of x is equal to f of 2x squared. Okay, that's a universal law. Okay, it's true for any x. So therefore we get, we can plug in 2x squared. So we're going to get 2x squared plus 1 divides f of 2x squared minus f of 1, right? That's true. Okay, that's a special case for x is replaced by 2x squared. But then of course f of 2x squared is just equal to f of x. That's what we just saw. Infinitely many values of f are equal. That was a crucial observation we made. So that's just f of x. So f of x minus f of 1 is in fact divisible by 2x squared plus 1. But we can keep going with this. We can now replace 2x squared. You can now take 2 times that thing squared. So if you square 2x squared, you get 4x to the 4 times 2 is 8x to the 4. So we then get 8x to the 4 plus 1 divides f of x minus f of 1. And as you can see, this keeps on going, which means that f of x minus f of 1 is divisible by arbitrarily large numbers. What positive integer is divisible by infinitely many other positive integers? None, okay? The only possibility, or what integer, okay? What integer is divisible? The only possibility is 0. Okay, so 0, that means f of x minus f of 1 has to be 0. So f of x is equal to f of 1, and that is true for all x, okay? That is independent of, whatever like x is, f of x has to equal to f of 1. So therefore, that implies that f is a constant function. And then finally, we have to actually check that constant functions work. And if we think about our functional equation, if we set f of x is a constant, f of x is some constant c for all x, okay, c is a constant, then the equation is true because x f of y plus y f of x is just going to equal to, so this is just going to equal to what? It's going to equal to x plus y times c. It's going to be c times x plus y. And the right-hand side of our functional equation was x plus y times f of x squared plus y squared. And of course, that is also going to, f of x squared plus y squared is just going to equal to c. So that's going to equal to, again, c times x plus y. So we're getting the same thing on both sides. So constant functions are the only functions that satisfy this equation, and they do satisfy this equation. And I've got 2 fun videos for you. So the first video is, if you're interested in more number theoretic ideas, here's a really beautiful puzzle. It's so fun. 2 power 29 has 9 distinct digits, okay? So you can write them down, okay? There are 9 distinct digits. And so they're numbers 0, 1 through 9. So the possible digits are 0, 1 through 9. 9 of them appear. There are 10 in total. Which one is missing? Can you find it out without a calculator or without calculating 2 power 29? Just by sleuthing. Check out this video. It's going to pop up on the screen. Very popular video on my channel. It's a beautiful puzzle. You're going to love it. And another fun video you're going to love is the inverse Pythagorean theorem, where you have a right triangle and you have this side that kind of creates a right angle here, and the side length is d. There is a beautiful relationship that 1 over a squared plus 1 over b squared is 1 over d squared. Want to see the proof and intuition? Check it out here. Have an amazing day.